To understand the farthest corners of the universe, we looked billions of light years away. We wrote the most complex models. But we found the greatest crisis in a discrepancy that has been right in front of our eyes for decades: the expansion rate of the universe. Two ultra-precise measurement methods are giving us two different speeds for the universe, and this difference is no longer an error, it is a crisis at the 5 sigma level. Because this crisis might be showing that the universe is not actually expanding equally in all directions. This is why colossal structures like 3.3 billion light-years, which exceed the 1.2 billion light-year limit, can form. And this is why we can observe a wall 15 billion light-years long in a 13.8 billion-year-old universe. But the real irony is that these anomalies are not independent of each other. They all point in the same direction. If you want to see how the pieces of this great cosmic puzzle come together, join the channel and turn on notifications, because this video is the story of how we shattered our most fundamental assumption about the universe. We're beginning. For years, we thought the universe was smooth on the largest scales. We believed that if you looked at two different points, billions of light years apart, you would statistically see the same thing. This idea was the bedrock upon which modern cosmology was built. But the James Webb telescope looked into the darkness, and what it saw in that darkness shook this bedrock to its core. We now know that one of the most fundamental assumptions we thought we knew about the universe is shattering before our very eyes. Therefore, to understand these discoveries that are demolishing everything, we first need to understand that fundamental assumption. Scientists call it the cosmological principle. It may sound complex, but it's based on a very simple idea. If you zoom out far enough, the universe looks the same everywhere. If you spread matter over a large enough area, everything averages out. There is no special region. There is no preferred direction. The universe is fundamentally homogeneous. This is the foundation beneath every equation, every simulation, and every model that cosmologists have built for the last 300 years. Because, without this idea, it would become impossible to mathematize the universe as a whole. Isaac Newton was the first to state this idea clearly in 1687. He wasn't talking about telescopes or galaxies at the time. He was just writing about how gravity fills space. But the assumption buried deep in his mathematics was precisely this. Matter is distributed evenly throughout the universe. The universe has no significant center or edge. You don't find a giant clump on one side and an empty void on the other. Einstein used the same idea when he formulated his equations for an expanding universe. Every cosmologist after him followed suit, and for a very long time, this idea seemed to be correct. The universe really did look smooth. The cosmic microwave background radiation, the faint afterglow of light left over from just after the Big Bang, was nearly identical in every direction. But if this smoothness was a principle, then there had to be a limit to the structures that could form within the universe. This is where the story breaks. Because this limit is not a guess, it's not a rough estimate at all, it is based on a specific calculation made by specific researchers in a specific year. These researchers did a numerical breakdown of how the universe builds structure over time. Imagine the universe just after the Big Bang. Everything is almost perfectly smooth. There are tiny differences in density, smaller than 1 in 100,000. Some points have slightly more matter, some have slightly less. Gravity gets to work. The denser regions pull in more matter. Over millions, then billions of years, these small clumps grow into stars, galaxies, clusters, and the vast cosmic web we see today. This process takes time, and time is the most fundamental constraint. Because gravity moves at the speed of light, a gravitational influence cannot travel faster than that. Therefore, a region of space can only pull in matter from a distance that light could have traveled since the beginning of the universe. Cosmologists call this the horizon scale. It is essentially the speed limit for how large any connected, coherent structure can grow. This is exactly where Yadav and his colleagues stepped in 2010. They used the standard Lambda-CDM dark matter model, the accepted framework for how the universe evolves. They calculated how fast density fluctuations could grow, how quickly gravity could assemble matter, and what the realistic upper limit on structure size would be. Their answer came out to about 370 megaparsecs. In more familiar terms, that's 1.2 billion light-years. This is the physical ceiling. Anything larger than this simply has not had enough time to form under the rules of standard cosmology. 1.2 billion light-years sounds enormous, and it is. It would take 1.2 billion years to cross this distance at the speed of light. The dinosaurs went extinct 66 million years ago. 1.2 billion years is almost 20 times that. Therefore, the existence of this limit was one of the most robust predictions of cosmology. But, when telescopes turned to the sky, they started finding things that shattered this prediction. Structures. Massive ones. Galaxy filaments stretching for distances that were impossible according to the cosmological principle. And each time they found one, they told themselves it might be a mistake, a statistical anomaly, a one-off fluke. Then they found another one, and another, and another. Right now, there are 7 confirmed structures that exceed the theoretical size limit. 7 data points, all pressing against the same boundary, and that boundary is no longer holding. Because the structures being found are not just slightly over this limit, they are double, triple, some are even 8 times larger. And the telescope at the center of each new discovery is the James Webb Space Telescope, a machine so powerful it can see back to a few hundred million years after the Big Bang, and a machine that, since its launch in December 2021, has been sending back data that makes it harder and harder every day to defend the standard model. Cosmologists aren't panicking in public, but they are publishing papers with titles like Strong Tension with Standard Cosmology. They are using the word crisis. They are asking if the model is broken. Because a telescope found something that shouldn't be there, a galaxy ring 1.3 billion light-years wide, and right next to it, a curved wall of galaxies 3.3 billion light-years long, both hanging in the same patch of sky. Both impossible. Therefore, all this evidence raises one uncomfortable question. If the most fundamental principle of the universe is wrong, and the calculated ceiling for the largest structures is being repeatedly broken, then how do we figure out what's wrong with our picture of the universe? These discoveries didn't come from the grand projects of senior scientists with decades of experience. Because the first person to find these impossible structures wasn't a professor. She was a student, still working on her doctorate, using a technique no major survey had ever applied. She wasn't looking for something impossible, she was just following the data, and the data led her somewhere. And the data led her to a place that made the entire field stop and take notice. Alexia Lopez was a PhD student at the University of Central Lancashire in the UK. She wasn't working on a grand project to overthrow cosmology. She was just doing what graduate students do. She had a dataset, a question, and a method. The unusual part was the method. Because, to find large structures in space, most astronomers map visible galaxies. You track where galaxies cluster and look for patterns. But Lopez was doing something different. She was using quasars as backlights. Quasars are the brightest objects in the known universe. They are the centers of distant galaxies where supermassive black holes are actively feeding, outshining entire galaxies of hundreds of billions of stars. Because they are so bright, they can be seen from across almost the entire observable universe. As the light from a quasar travels towards us, it passes through any matter that lies between us. If there is a gas cloud, a galaxy filament, a large structure in the way, the light from the quasar will be slightly absorbed by that matter. Specifically, a type of ionized magnesium in the gas leaves a distinct chemical fingerprint in the quasar's light spectrum. Lopez mapped these fingerprints. She was charting the places where intergalactic gas and matter were dense enough to leave a mark on the quasar light. And in 2021, a shape appeared in her maps that she couldn't immediately explain. A curved arc. It was huge. It stretched across a region of the sky about 10 degrees wide. If it were visible to the naked eye, it would cover the width of 20 full moons lined up side by side. But it was sitting 9.2 billion light-years away, so no human eye will ever see it directly. Lopez measured it from one end to the other as 3.3 billion light-years. That was nearly 3 times the theoretical maximum size for any structure in the universe. She named it the Giant Arc. She announced it at a major astronomy conference in June 2021. The reaction wasn't one of dismissal. It wasn't one of celebration either. It was one of careful, serious interest. Because if this structure was real, it was a problem. A major problem. Some researchers suggested it could be a statistical fluke. When you look for patterns in a large dataset, you run the risk of finding shapes that aren't really there. This is known as the look elsewhere effect. The more area you search, the more likely it is that a random clustering will mimic a structure. Lopez ran the statistics. The probability of the giant arc appearing by chance was calculated to be about 1 in 100,000. That was a strong signal. A signal strong enough that it would have to be refuted not just with skepticism, but with actual evidence. But there was something that made her findings even harder to ignore. 2 years later, she found something else in the same region of the sky, and this second structure was somehow even more inexplicable than the first. It wasn't another arc. It was a ring, a perfect ring of galaxy clusters 1.3 billion light-years in diameter. It was hanging in the same cosmic neighborhood as the giant arc, and its statistical significance came out even higher. The fact that she had found 2 impossible structures in the same patch of sky, at the same cosmic distance, using the same technique, was something no standard model predicted. There was something out there waiting to be found, and she had found it. Twice. Therefore, to grasp what these structures mean, we have to visualize their scale in our minds. Close your eyes and imagine the largest thing you have ever seen. Maybe a mountain range, a storm system from an airplane window, the horizon itself. Now try to scale that up. Keep scaling past countries, continents, the entire Earth, the solar system, the distance to the nearest star. Keep going for a 3.3 billion year journey of light. That is the giant arc. It's a curved structure, not a straight line. Not a random blob, a genuine arc. Like the top half of a circle, built from clusters of galaxies woven together by filaments of gas and matter. These galaxy clusters are themselves massive objects. A single galaxy cluster can contain thousands of individual galaxies. Each galaxy is home to hundreds of billions of stars, and the giant arc links many of these clusters together along a curved path 3.3 billion light-years long. That shape is the first mystery. Because, in physics, arcs appear when something bends space, or when 2 objects interact in a specific geometry. On small scales, we see arcs all the time in a phenomenon called gravitational lensing, where the gravity of a massive object bends the light from something behind it into a curved line. But the giant arc is not a lensed image. It's a real physical structure made of real matter, curving over a region of space so large that it defies the standard explanation for why curves appear in galaxy distributions. The second mystery is what it's made of, or rather, what is holding it together. Because a structure this large should not be gravitationally coherent under the rules of standard cosmology. Gravity works slowly. Over billions of years, it builds galaxy clusters, then chains of clusters called superclusters, and then the largest confirmed structures called filaments and walls. But there's a speed limit on how far its influence can reach in a given amount of time. The giant arc is simply too long for gravity to have assembled it from one end to the other in the time available. So, either gravity behaved differently in the early universe than our models predict, or the giant arc was formed by a process we haven't yet identified, or there's a fundamental flaw in our models of structure growth. None of those options are comforting. We now know what the cosmological principle means, where the size limit comes from, and how and where Alexia Lopez shattered it. But this was only the beginning. Because, as strange as the giant arc was, it turned out to be the smaller of the 2 structures Lopez would find, and the second one had a shape that made even less sense. 2 years later, in January 2024, Lopez stood up with something she now called the Big Ring. Now we're going to leave all this theoretical groundwork behind and focus on what the telescopes are actually seeing. Because the data coming back from James Webb isn't just about large structures, it's also about galaxies that formed too early and are too developed to be there. And one of those galaxies has the potential to upend our entire timeline. But we're not wondering anymore, because the real findings are far beyond the theoretical limits. And now comes the real shock. What Webb found isn't just one, it's two massive impossible structures, in the same corner of the sky at the same time. Here are the findings and how the standard model is left helpless in their wake. 2 years after the giant arc, Alexia Lopez stood up in front of a room of astronomers at the 243rd meeting of the American Astronomical Society. The date was January 2024, and she had something new. She called it the Big Ring, but that name doesn't quite do it justice, because this was a ring of galaxy clusters 1.3 billion light-years in diameter. Its circumference was about 4 billion light-years. To put that circumference into perspective, 4 billion light-years is longer than the giant arc itself. The entire 3.3 billion light-year long giant arc could fit inside the outer edge of the Big Ring, and there would still be room to spare. And the Big Ring was sitting at the exact same distance from us as the giant arc, 9.2 billion light-years away. Same cosmic epoch, same cosmic neighborhood, separated by only 12 degrees in the sky. That's about the width your hand and a half would cover in the night sky at arm's length. Two impossible structures. Same place, same distance, same researcher. The shape of the Big Ring is what makes it even weirder than the giant arc. Because while a filament or an arc is unexpected at this scale, it at least fits the general architecture of the cosmic web. The universe makes walls and filaments. They can be big, it's just a matter of scale. But a ring is different. Therefore, when scientists first saw it, only one plausible explanation came to mind. Rings in galaxy distributions are known to form from one specific process: baryon acoustic oscillations. These are pressure waves that rippled through the early universe in the first moments after the Big Bang. Like sound waves moving through a fluid, they spread out in all directions. And when the universe cooled and matter decoupled from radiation, they froze in place. This frozen ripple shows up in galaxy surveys as a faint spherical shell about 1 billion light-years in diameter. Cosmologists use these shells as a standard ruler to measure cosmic distances. They are well understood and well verified. But the Big Ring is too big. The standard baryon acoustic oscillation shell size is about 1 billion light-years. The Big Ring's diameter is 1.3 billion light-years. And more importantly, Lopez looked at its three-dimensional shape. It looks like a ring when viewed from above, but in 3 dimensions, it's more like a corkscrew, a helical twist. Baryon acoustic oscillations produce spherical shells. They do not produce corkscrews. So, the only standard model explanation available for ring-like galaxy structures does not fit the Big Ring. This leaves the field in a truly uncomfortable position. You have an object with a confirmed shape, a confirmed size, and a statistical significance that is over the gold standard threshold for a real discovery, and there is no accepted explanation for how it formed. But the real question is, how do we know this ring is real? How do scientists tell the difference between a real cosmic structure and a pattern that our brains invent by staring at random dots for long enough? The answer is statistics, and the Big Ring clears that bar, because in physics and astronomy, there is a standard for calling something a real discovery. Scientists measure significance in units called sigma. 1 sigma means the result is slightly unlikely to be by chance. 3 sigma means the odds of it being a coincidence are roughly 1 in 1,000. 5 sigma is the gold standard. At 5 sigma, the probability of random chance producing the same result drops below 1 in 3 million. That is the level at which physicists declared the Higgs boson to be real. It is the threshold the entire field uses to say, This is not noise. The Big Ring scored 5.2 sigma. That means the odds of it appearing in the data by random chance alone, without a real physical structure behind it, are less than 1 in 3 million. Lopez and her colleagues used not just one, but multiple independent statistical tests to arrive at that number. But Lopez didn't stop. Because the giant arc and the Big Ring, as strange as they were, might have just been pieces of an even larger structure. In April 2026, Lopez and her colleague Roger Clowes submitted a new paper to arXiv, the open-access scientific archive where researchers share findings before formal peer review. The title was direct: A Giant Ring on the Sky. This wasn't a new structure discovered in a different part of the universe. This was a realization about the same region they had been studying, a realization that what they had found before were not two separate anomalies, but a single massive structure, and they had only been seeing parts of it. The key was a filament they called the Northern Arc. In their earlier work, Lopez had identified this curved feature sitting above and around the Big Ring. When she traced its path fully, it turned out it could connect to the giant arc. Following this connection, the two arcs together formed a ring so large that it encompassed the entire Big Ring within its circumference. They called this the giant ring on the sky. They used two independent methods to check if the structure was statistically real. Both methods found features that exceeded 4 sigma. That is a strong threshold, serious enough to be taken seriously even if it is below the 5 sigma gold standard. But the most striking result came from simulations. They applied it to the Flamingo 10,000 simulation, one of the most detailed computational models based on standard cosmological physics. In every single patch of the universe that Flamingo 10,000 produced, the clustering pattern of the giant ring on the sky did not appear. Not once. In no version of the simulated universe did the physics produce anything that looked like the giant ring on the sky. This means the structure is not only statistically present in the data, it is statistically absent from every version of the standard model universe that computers can build. And that brings us to the inevitable question: if our standard model can't explain these structures, what can? Therefore, scientists are having to look outside of mainstream physics. And the first candidate that comes to mind sounds like something out of science fiction: cosmic strings. Imagine the universe just after the Big Bang. Temperatures are unimaginable. All the fundamental forces of nature are unified into a single force. Then as the universe expands and cools, these forces separate. Physics calls these separations phase transitions, and they are roughly analogous to water turning into ice. When water freezes, it doesn't all freeze into a perfect crystal at once. Ice crystals form in different places and grow towards each other. Where two crystals meet from different directions, a boundary line is formed, a place where the crystal structure doesn't quite line up. That boundary is a defect in the ice. The same thing may have happened in the very early universe. As the unified force split into separate forces, different regions of space may have transitioned at slightly different rates or in slightly different orientations. Where these regions met, a defect in the very fabric of space could have been left behind. These are called topological defects, and one class of them, called cosmic strings, would take the form of a one-dimensional line stretching across space. An infinitely thin filament with an immense concentration of energy packed into it. How thin? Smaller than a proton. The width of a cosmic string, if it exists, is far below anything you could ever see with any instrument. But the energy packed into that line is extraordinary. A single inch of a cosmic string would weigh more than a mountain range, and a cosmic string stretching for billions of light years would carry a gravitational influence that could have gathered matter along its path over the lifetime of the universe. This gravitational influence could have triggered the formation of galaxies in the shape of arcs and rings. If a cosmic string existed in the region around redshift 0.8, its gravity would have pulled matter along its length, and galaxies would have formed in curved patterns that followed the shape of the string. A corkscrew-shaped string would produce a corkscrew-shaped ring of galaxies. An arc-shaped string would produce an arc of galaxy clusters. This is a confirmed theory in the sense that cosmic strings are a legitimate prediction of certain models of early universe physics. They arise naturally from quantum field theories and string theory models of how the universe began. However, the physical evidence for cosmic strings is scarce. We have not detected one directly. We have not seen a definitive gravitational effect that could only be explained by a cosmic string. But now we have arc and ring structures in the universe that no standard model process can produce. And the description of what a cosmic string would leave behind sounds a lot like what has been found. This does not make cosmic strings confirmed, but it makes them the most physically motivated explanation available for structures that currently have no other explanation. But even cosmic strings are only part of the equation, because the Webb telescope isn't just finding structures that are too big, it's also finding galaxies that formed too early. And one of those galaxies is strange enough to call the entire standard timeline into question on its own. The James Webb was launched on December 25, 2021. It travelled 1 million miles from Earth to a stable gravitational point, where it could remain fixed relative to the Sun and Earth. The alignment process took months. Engineers checked the mirrors, calibrated the instruments, and tested every system. When the first science images were released in July 2022, the performance was described by mission scientists as good, if not better, than the most optimistic predictions that everyone has. That was the telescope side of the story. The science side began almost immediately. Before Webb, cosmologists had a confident picture of how the early universe worked. In the first few 100 million years after the Big Bang, the universe was filled with hydrogen and helium gas. Gravity slowly pulled this gas into the first small stars, which formed in small, chaotic clouds. These clouds merged into slightly larger structures over hundreds of millions of years. It took billions of years for large, well-formed galaxies to come together. Finding a large, mature galaxy any earlier than about 1 billion years after the Big Bang was considered extremely unlikely. Webb started finding them immediately. Galaxies at redshifts over 7, over 10, even over 12. This means they existed less than 400 million years after the Big Bang, some even less than 300 million years. And these weren't small, chaotic proto-galaxies. Some were massive, some were bright, some were already showing signs of being mature systems with established star populations and chemical enrichment that takes time to build up. The numbers were jarring. The standard model predicts how many massive galaxies there should be at these cosmic distances. Webb was finding roughly 10 times more at the largest distances than predicted. 10 times more than the equations said should be there. The researchers were careful. The first reaction was to check the data. Were the redshifts confirmed? Were the mass estimates reliable? Could something about the way Webb was observing these galaxies make them appear larger or more numerous than they really were? Some of the discrepancy was explained by updated calibrations. Some of the early mass estimates were revised downwards. But even after accounting for measurement uncertainties, a real tension remained. The galaxies were there. There were more of them than the standard model predicted, and they were bigger and more mature than they should have been at the age Webb saw them. One team, publishing in a major journal, described their observations as being in strong tension with standard cosmology. But the galaxy that best summarizes the problem with the standard timeline wasn't found in a survey. It was found by accident. And this one galaxy could change the whole story. So how does the mechanism behind all these discoveries work? To understand why the James Webb's early galaxy discoveries are so unsettling, you need to understand what the standard model actually predicts about the first billion years of the universe. Now we're going to step back from the shocking findings for a moment and drill down into the fundamental physics that makes them possible, and also makes them a problem. Because the problem isn't with the telescope, it's with the theories we use to explain what the telescope sees. The framework for this theory is called lambda cold dark matter. Lambda refers to the cosmological constant, the term Einstein added to his equations to describe dark energy, the force that is accelerating the expansion of the universe. The cold dark matter part refers to the dominant type of matter in the universe, a form of matter we can't see or touch, but that exerts gravity and drives structure formation. In this model, structure grows from the bottom up. The smallest clumps of dark matter form first, Then gravity pulls these clumps into larger ones, and then into even larger ones. Galaxies form inside the dark matter clumps. Small galaxies merge into larger ones over time. Massive galaxies are the end product of a long chain of smaller mergers and gas accretion. This process has a speed. It operates at the rate at which gravity can assemble objects over cosmic distances, and at the highest redshifts, when the universe is only a few 100 million years old, the model calculates what mass the most extreme galaxies should have reached by that point. It sets a ceiling. For galaxies more massive than 10 billion times the mass of the Sun, at redshifts above 7, the ceiling is essentially 0. In the Standard Model, there simply has not been enough time for that much matter to have accumulated in one place, through the slow, merger-driven process the model describes. But Webb found a population of them. This doesn't automatically mean the Standard Model is wrong, because scientists have proposed several alternative explanations that remain within conventional physics. One possibility is that early star formation was much more efficient than models assume. If stars converted gas into stellar mass more rapidly than expected, that could make galaxies appear larger than the model predicts, without requiring any new physics. Another possibility involves the initial mass function, which describes what mix of small, medium, and massive stars a galaxy tends to produce. If early galaxies formed more massive stars than modern ones, each burst of star formation would produce far more light and mass than current models expect. A third explanation involves black holes. If supermassive black holes existed earlier and were more active in the first billion years, the radiation they produced could have shaped star formation in ways that made galaxies appear larger or brighter than their true mass. These are all legitimate hypotheses. Researchers are actively testing them, and the masses of some of the most extreme early galaxy candidates from Webb's initial observations have been revised downward after more careful analysis. But a real tension persists. Even the conservative mass estimates for some of Webb's early galaxy detections still sit above what the Standard Model can comfortably allow. The picture hasn't been overturned, but it has been stretched. And the single galaxy that best illustrates this tension wasn't found by searching for early universe anomalies. A scientist pointed Webb at something nearby, and this thing showed up in the background without warning. In 2024, a group of astronomers were using the James Webb to study a quasar. Quasars are good targets for detailed observation because they are so bright that the light they produce can be used to probe the gas and matter in their immediate surroundings. The researchers pointed Webb at the quasar, started collecting data, and something appeared in the field of view that had nothing to do with what they were looking for. A spiral galaxy. A massive one. It was sitting behind the quasar, in the background. A fully formed disk system with clearly structured, clearly massive, clearly spiral arms. This was unusual. A galaxy this large and this well organized was not expected to show up at this cosmic distance. The team spent time confirming what they were seeing, measuring its redshift to determine how far away and how old it was. The answer placed it 11.7 billion light-years from Earth. Given the age of the universe, this means we are seeing this galaxy as it was about 2 billion years after the Big Bang. 2 billion years after the Big Bang is early, very early. At that point, according to the Standard Model, galaxies were still relatively young and relatively small. The merger-driven growth process described by Lambda-cold dark matter hadn't had enough time to build something on this scale. They named it the Big Wheel. Published in the journal Nature Astronomy in March 2025, the Big Wheel was described as one of the largest spiral galaxies ever found, and a galaxy of this size was not expected to be fully assembled in such an early epoch of the universe. The lead researcher, Charles, from Caltech, noted it was unprecedented for this early period of the universe. The discoverers were not shy about the implications. Co-author Sebastiano Cantalupo from the University of Milan said that typically it would take the entire age of the universe for a galaxy to grow this large. They were seeing something that the standard developmental timeline did not predict. The Big Wheel also showed a spiral structure, defined arms, a disk shape. These are characteristics of mature, settled galaxies. Young galaxies, especially at early cosmic times, tend to be irregular, clumpy and asymmetric. They haven't had time to organize themselves into the smooth, rotating disk structure of a classic spiral. But the big wheel had exactly this structure 2 billion years after the universe began, and it was found by chance. The telescope was pointed for a completely different object, which raises the uncomfortable question. If an anomaly this significant can show up unexpectedly in a single quasar field, how many more are sitting unnoticed in the vast sky that Webb has not yet surveyed? And now, the structure of the big wheel isn't just surprising. A feature within it, the way its stars move, is particularly difficult to explain within the standard timeline. And that brings us back to a problem that led to one of the biggest pieces of evidence for all of modern cosmology: the existence of dark matter. Therefore, when astronomers measure a galaxy, one of the most revealing things they can look at is how fast its different parts are rotating. In the solar system, planets closer to the Sun orbit faster than those farther out. Mercury orbits in 88 days. Neptune takes 165 years. The closer you are to the central mass, the faster the orbit. This is basic gravity. If galaxies worked the same way, stars near the center would orbit quickly, and stars in the outer disk would orbit slowly. For most of the 20th century, astronomers expected this. Then they measured it. The outer stars in galaxies are not slow. They orbit at nearly the same speed as the inner ones. The rotation curve, a graph of orbital velocity versus distance from the center, is flat. This was one of the key pieces of evidence that led to the suggestion of dark matter. Because an invisible mass must be distributed throughout the galaxy, keeping the outer stars moving fast even though they are far from the visible center. Flat rotation curves are a hallmark of mature, fully assembled galaxies. They indicate that a galaxy has formed its full dark matter halo, the invisible shell of dark matter that surrounds the visible disk, over billions of years of growth and merger activity. And the big wheel has a flat rotation curve, 2 billion years after the Big Bang. This is highly unexpected. Because building a full dark matter halo takes time. The merger-driven growth process of the Standard Model predicts that halos at this cosmic age would still be in the process of assembling, still pulling in surrounding matter, and still far from the stable, extended distribution that produces a flat rotation curve. The research team compared the big wheel's rotation to the Tully-Fisher relation. This is a well-established relationship between how fast a galaxy rotates and how bright it is. The Tully-Fisher relation is calibrated using galaxies in the modern universe. Galaxies billions of years older than the big wheel, local galaxies, nearby galaxies, galaxies that have had the entire age of the universe to grow. The big wheel fits the same relation. It is rotating at the speed of a mature, fully grown galaxy. It has the brightness of a mature, fully grown galaxy. It has the mass of a mature, fully grown galaxy, and it existed when the universe was only 14% of its current age. The research paper described it as a true outlier, even compared to other massive galaxies from the same early cosmic epoch. Something reached full galactic maturity in a tiny fraction of the time the Standard Model allocates for this process. This deepens the big wheel problem. Because the Milky Way is not a small galaxy, it contains between 100 and 400 billion stars. Its disk stretches for about 100,000 light-years. It has a central black hole that weighs 4 million times the mass of the Sun. It took roughly 13 billion years to get to where it is today. But the big wheel is 5 times more massive. That means 5 times more stars, 5 times more stellar mass, and a dark matter halo to scale. And it assembled all of this in 2 billion years, less than 1/7 of the time it took the Milky Way. In other words, if the Milky Way's growth took 13 years, the big wheel reached 5 times that size in about 1 year and 8 months. The Standard Model has no mechanism that works that fast. The Lambda cold dark matter framework builds galaxies through mergers and gradual gas accretion. Smaller structures merge with larger ones, which merge with even larger ones. Each merger takes hundreds of millions of years. Each phase of gas accretion for the gas to cool, collapse, and form stars takes time. The process is continuous, but slow. Therefore, to solve this problem, some researchers are advocating for modified star formation rates. They say early galaxies may have formed stars at much higher rates than anything seen in the modern universe. If gas in early galaxies collapsed and turned into stars more efficiently, you could build more mass in less time. This is physically possible. Because early galaxies existed in denser environments with more gas and different cooling conditions, the star formation rates in some observed early galaxies are already much higher than typical local rates. But even if you push star formation efficiency to its theoretical limits, models struggle to produce the mass of the big wheel at its age. The paper's authors noted that its size was at least 3 times larger than what cosmological simulations predict for a galaxy of similar mass at that epoch. And the big wheel is a single galaxy, a known object, something Webb found by accident. The question the field is wrestling with is whether this is a rare, extreme outlier, or a sign that early galaxy formation is systematically different from what the standard model predicts. All these technical details, flat rotation curves, the Tully-Fisher relation, the lambda cold dark matter model, are all pieces of one big picture. On one side, you have an incredibly successful theory that tells you how the universe should work. On the other, you have a growing number of observations that refuse to fit that theory. Massive structures, early galaxies, unexpected rotation speeds. They all point in the same direction. But what's truly exciting is that these problems aren't independent of each other. Because there is a larger, more fundamental problem that might unite all of these anomalies under one roof and shake cosmology to its foundations. A crisis. And that crisis stems from a measurement of the universe's most basic property, how fast it is expanding. But what's truly exciting is where all these pieces come together. Because, now, we arrive at the climax of the entire video. The massive structures, the early galaxies, those were just the beginning. Now we're going to talk about the largest structure in the known universe, the oldest galaxy, and the one number that is shaking all of cosmology. The tempo is increasing, the findings are becoming more shocking, and now, the most incredible thing has happened. Everything we've discussed so far was big, uncomfortably big, but the Hercules Corona Borealis Great Wall is in a different category. It is, by current measurements, the largest known structure in the observable universe, and its size is not just impressive, it's physically destabilizing. This Great Wall stretches for roughly 10 billion light-years from one end to the other. 10 billion light-years. It would take 10 billion years to cross it at the speed of light, the fastest anything can move in the universe. The universe itself is only 13.8 billion years old. A photon that started at one edge of the Hercules Corona Borealis Great Wall at the moment of the Big Bang would not have reached the other side yet. The cosmological principle's maximum structure size is 1.2 billion light-years. But the Great Wall is more than 8 times larger than that limit. If the cosmological principle is a football field, the Great Wall stretches to the parking lot 8 fields away. It was discovered in 2014 not by mapping galaxies directly, but by tracking something even more dramatic: gamma-ray bursts. These are the most energetic explosions in the known universe. When a massive star dies in a specific way, it releases more energy in seconds than the Sun will emit over its entire 10 billion year lifetime. They are so bright they can be detected from across almost the entire observable universe. Therefore, if the universe is homogeneous, gamma-ray bursts should be distributed evenly across the sky. But in a specific region of the sky, in the direction of the constellations Hercules and Corona Borealis, there was a concentration of gamma-ray bursts so dense it could not be random. The clustering was statistically significant, and tracing the region where the bursts clustered revealed a galaxy filament structure stretching over a region 10 billion light-years long. The discovery was immediately controversial. Some researchers accepted it as a real structure. Others argued that gamma-ray bursts are not reliable tracers of the underlying galaxy distribution, that their detection is affected by observational biases that could mimic a clustering signal. The debate was not fully resolved, But in April 2025, a team published updated measurements using a much larger sample of 542 gamma-ray bursts with confirmed redshifts. Their results were stunning. The structure might be even larger than the 2014 estimate. The new data suggests it could span from redshift 0.33 to 2.43. That is a range that corresponds to roughly 15 billion light-years in cosmic depth. 15 billion light-years. Larger than the distance light has travelled since the Big Bang. A structure larger than the age of the universe. This exceeds the limit of the cosmological principle by a factor of 12. This is a number that fundamentally breaks cosmology. But now, let's go to the other end of the scale. Not the largest structure, but the single galaxy at the most extreme distance Webb has ever confirmed. The universe was 280 million years old. In cosmic terms, this is barely a breath after the Big Bang. The first stars had only just ignited. The first galaxies were just beginning to form from collapsing clouds of hydrogen and helium gas. The universe was dark and chaotic, lit only by the first fragile points of starlight scattered across an endless sea of gas. And yet, a galaxy was already there. Not a proto-galaxy, not a fragmented cloud. A galaxy with measurable chemical enrichment, with starlight bright enough for the James Webb to detect from 13.5 billion light-years across space, with a spectrum detailed enough to reveal what its stars were made of. Scientists named it JADES-GS-Z14-0. NASA confirmed its detection in early 2026, calling it one of the most distant galaxies ever spectroscopically confirmed. Spectroscopic confirmation is the gold standard for distance measurement in cosmology. To take a spectrum is to break the light from an object into its component wavelengths and read the chemical signatures embedded within. Different elements absorb and emit light at specific wavelengths, like fingerprints. By reading these fingerprints and measuring how much they have been stretched by the expansion of the universe, scientists can calculate exactly how far away and how long ago the light was emitted. The spectrum of JADES-GS-Z14-0 confirmed it without a doubt. This galaxy existed 280 million years after the Big Bang, but JADES-GS-Z14-0 carried a detail in its spectrum that elevated it from remarkable to profoundly confusing. It showed nitrogen. Specifically, it showed nitrogen at a level far higher than expected for such an early galaxy. Because nitrogen is not a primordial element. The Big Bang produced hydrogen, helium, and trace amounts of lithium. Everything heavier, carbon, oxygen, nitrogen, iron, had to be forged inside stars and distributed into space when those stars died. That process takes time. Massive stars live fast and die young, so they can return elements to space within a few million years. But building up a significant amount of nitrogen enrichment throughout a galaxy requires multiple generations of stars to form, die, and seed the next generation. JADES-GS-Z14-0 shows a level of nitrogen enrichment that implies a richer stellar history than 280 million years should allow. This is not an isolated curiosity. It connects to a broader pattern that Webb keeps returning. The early universe seems more chemically evolved, more structurally mature, and more active in star formation than the standard timeline predicts. And this brings us to the moment where all these discoveries intersect, where all these anomalies converge into one massive crisis. The Hubble tension. There should be a single number that describes how fast the universe is expanding. This rate is called the Hubble constant. But the two different methods of measuring this number give two different answers, and the gap between them is too wide to be explained by measurement error alone. The first method uses the cosmic microwave background. This is a snapshot of the early universe. Fitting the standard cosmological model to this pattern gives a precise prediction for the Hubble constant, about 67 kilometers per second per megaparsec. The second method uses local measurements. Astronomers measure distances to nearby objects. When local measurements are used to calculate the Hubble constant, the answer comes out higher, about 73 kilometers per second per megaparsec. The universe is either expanding at 67 or 73. It cannot be both. For years, this was described as a problem. But in January 2025, a team led by Dan Skolnick at Duke University published a new measurement of the local Hubble constant. Their result? 76.5 kilometers per second per megaparsec. This was the highest local measurement ever, and it pushed the discrepancy between local measurements and the CMB prediction to a statistical significance level of over 5 sigma. 5 sigma. The same gold standard that confirmed the Higgs boson. Skolnick was clear about what this meant. He said the tension has now become a crisis. The standard model of cosmology may be broken, he said. A leading physicist describing the foundational framework of his field using the word broken. That is not casual language in science. It is a statement that the internal consistency of the model has failed at a level that requires a structural response. So what does this all mean? An expansion rate that looks different at different times. Structures that are too big to exist. Galaxies that are too early to exist. How do all the pieces of this puzzle fit together? Amounts of lithium. Everything heavier, carbon, oxygen, nitrogen, iron, had to be forged inside stars and distributed into space when those stars died. That process takes time. Massive stars live fast and die young, so they can return elements to space within a few million years. But building up a significant amount of nitrogen enrichment throughout a galaxy requires multiple generations of stars to form, die, and seed the next generation. JADES-GS-Z14-0 shows a level of nitrogen enrichment that implies a richer stellar history than 280 million years should allow. This is not an isolated curiosity. It connects to a broader pattern that Webb keeps returning. The early universe seems more chemically evolved, more structurally mature, and more active in star formation than the standard timeline predicts. And this brings us to the moment where all these discoveries intersect, where all these anomalies converge into one massive crisis. The Hubble tension. There should be a single number that describes how fast the universe is expanding. This rate is called the Hubble constant. But the two different methods of measuring this number give two different answers, and the gap between them is too wide to be explained by measurement error alone. The first method uses the cosmic microwave background. This is a snapshot of the early universe. Fitting the standard cosmological model to this pattern gives a precise prediction for the Hubble constant, about 67 kilometers per second per megaparsec. The second method uses local measurements. Astronomers measure distances to nearby objects. When local measurements are used to calculate the Hubble constant, the answer comes out higher, about 73 kilometers per second per megaparsec. The universe is either expanding at 67 or 73. It cannot be both. For years, this was described as a problem. But in January 2025, a team led by Dan Skolnick at Duke University published a new measurement of the local Hubble constant. Their result? 76.5 kilometers per second per megaparsec. This was the highest local measurement ever, and it pushed the discrepancy between local measurements and the CMB prediction to a statistical significance level of over 5 sigma. 5 sigma. The same gold standard that confirmed the Higgs boson. Skolnick was clear about what this meant. He said the tension has now become a crisis. The standard model of cosmology may be broken, he said. A leading physicist describing the foundational framework of his field using the word broken. That is not casual language in science. It is a statement that the internal consistency of the model has failed at a level that requires a structural response. So what does this all mean? An expansion rate that looks different at different times. Structures that are too big to exist. Galaxies that are too early to exist. How do all the pieces of this puzzle fit together? Therefore, in late 2024, a research paper appeared on Archive with a sharp title. Its argument was that the Hubble tension, the discrepancy in expansion rate measurements, might not be caused by a problem with the physics of dark energy or neutrinos. It might be caused by a violation of the cosmological principle itself. The logic works like this. The CMB measurement of the Hubble constant assumes the universe is the same in all directions. The calculation uses the Standard Model's assumption of homogeneity and isotropy. If the universe actually has a preferred direction, if it is not perfectly smooth on the largest scales, then the CMB calculation is based on a flawed assumption, and its estimate of the Hubble constant would be systematically wrong. In contrast, the local measurement uses distances and recession velocities measured in our cosmic neighborhood. If the region of the universe we live in has a slightly different expansion history than the average, for example, if we are sitting in a large, low-density void that drives faster local expansion, or if our local region is embedded in a structure that skews our measurements, then the local Hubble constant would also deviate from the true cosmic average. Both measurements could be correct in their own frame of reference and still disagree if the universe is not truly uniform. The disagreement, then, would be a signal that the universe has a large-scale structure, a preferred direction, or a regional variation in its expansion rate that the Standard Model does not include. This would mean the Hubble tension and the excessively large structures, the giant arc, the big ring, the Great Wall, are symptoms of the same underlying condition. The cosmological principle isn't just approximately wrong at the scale of individual structures, it is wrong at a level that impacts the global expansion history of the universe. This is a theory, not a confirmed result, but the connection it draws is specific and testable. If the universe has a preferred direction, then surveys that measure the distribution of galaxies in different directions should detect a systematic asymmetry. And there is growing evidence that exactly this kind of asymmetry has already been found. This brings us to one of the most unsettling and persistent anomalies in cosmology, the axis of evil in the cosmic microwave background. The CMB is the most studied dataset in cosmology. The Standard Model predicts this map should look statistically random in all directions. The universe at that early moment should not have shown a preferred direction, but it does. Over years of analysis, several anomalies have been detected in the CMB. One is a hemispherical asymmetry. One half of the sky has slightly more temperature variation than the other. Another is the alignment of the largest features of the CMB, the quadrupole and octupole patterns. They should have pointed in random directions, but instead they appear aligned in a way that cosmologists have dubbed the axis of evil. A third is a statistical excess of even-numbered spatial patterns versus odd-numbered ones, a parity violation that the Standard Model does not predict. But the CMB is not the only place this preferred direction shows up, and this is where it becomes even harder to dismiss. Because multiple independent large-scale surveys of different types of objects have been analysed for what are called cosmic dipoles. This is a systematic difference in the number or brightness of objects seen in one direction of the sky versus another. The surveys include radio galaxies, infrared-selected objects, optical galaxies, and quasars. They use different wavelengths, different instruments, different selection methods, and different teams. They all find dipoles, and the dipoles all point in roughly the same direction. The expected dipole from our own motion, the kinematic dipole from the Milky Way moving through space, is well understood and accounted for. Even after subtracting it out, a significant residual dipole remains in all these surveys. A direction on the sky where the universe systematically looks different than from the opposite direction. The combined statistical significance of this preferred direction across all surveys has exceeded 5 sigma. 5 independent chains of measurement, all pointing in the same direction, at a level of confidence that in physics signifies a real physical discovery. If it is real, it is a direct violation of one of the 2 pillars of the cosmological principle, isotropy. The universe is not the same in all directions. It has an axis, a preferred orientation, and that fundamentally changes what kind of universe we live in. 5 independent surveys using different telescopes, different wavelengths, different types of objects, and different analysis teams all find the same preferred direction, with a combined significance of over 5 sigma. That is the state of the current evidence. And that leads us to one final epic discovery that ties all these pieces together. Just one map, but a map that shows the universe in a way we have never seen it before. In June 2025, astronomers released something that had never existed before. A map of the universe created from James Webb data that spanned almost all of cosmic time. It covered a region of the sky a little more than half a degree across, roughly the size of your thumbnail held at arm's length. In that thumbnail-sized patch of sky, roughly 800,000 galaxies. The project was called the Cosmic Evolution Survey, or COSMOS. It's a long-running collaboration that has used multiple telescopes over the years to survey the same patch of sky in ever-increasing detail. Webb's contribution, which required 255 hours of observation time, made the map the deepest and most complete ever. Kailton Casey from the University of California, Santa Barbara led the project. Her team described the results as startling, even for researchers who had been preparing for them for years. The surprise was the number of bright early galaxies at the largest cosmic distances. Webb found roughly 10 times more bright galaxies than theoretical models predicted before it launched. 10 times. The models weren't off by a small margin, they were off by an order of magnitude. The COSMOS map also revealed supermassive black holes that were invisible to Webb's predecessor, the Hubble Space Telescope. These black holes, sitting at the centers of early galaxies, were actively feeding and growing at distances and cosmic ages where the standard model did not expect them to be so numerous or so massive. Every additional galaxy in the map, every unexpected black hole, adds statistical weight to the same underlying conclusion. The early universe built structure faster and more efficiently than the lambda cold dark matter model predicts. This is a statement that something in a model is fundamentally underestimating how quickly the early universe built its large-scale architecture. And now, after all these epic, record-breaking, theory-shattering discoveries, it is time to pause and take a breath. Because these numbers, these distances, these crises are not just abstract scientific problems. They are questioning our most basic understanding of our place in the universe. So what does all this chaos mean for us? Now is the time to stop and to think. Because nothing Webb has found changes the Earth's orbit around the Sun. It does not change the speed of light. It doesn't change how atoms bond, how DNA replicates, or how gravity holds you to the ground. The physics of daily life, the physics of engineering, medicine, chemistry, and technology is built on scales far smaller than anything a cosmological model describes. So in a practical sense, a violation of the cosmological principle doesn't move the markets, it doesn't change the weather, it doesn't affect anything a human being experiences in a lifetime. But the implications are not absent, they just operate on a different scale, the scale of what we know and what we can build upon. And now we face the most important question. In a universe 15 billion light-years wide, what is the place of an average 1.7 meter tall human? This brings us to the first and most profound contrast, the unimaginable vastness of the universe and our immeasurable smallness. On one hand, there is the Hercules Corona Borealis Great Wall, stretching for 15 billion light-years, a structure that even light cannot travel across from one end to the other in the entire lifetime of the universe. And this is just one of 7 confirmed massive structures. On the other hand, there is you, a small speck of dust, on this planet, in this galaxy, in one of the countless galaxy clusters within this massive structure, orbiting one of the trillions of stars. How can these two realities exist at the same time? On one hand, near infinity, and on the other, near nothingness. There is a tragic side to this thought, because it reminds us of how physically insignificant we are. You and I will never reach those massive structures. We will never walk on the spiral arms of the big wheel galaxy. We will never see the light of the first stars of JADES-GS-Z14-0 with our own eyes. These distances are so vast that the human mind cannot fully comprehend them, and human technology cannot even dream of crossing them. We are trapped on a small island in this cosmic ocean, and the other side of the ocean will forever remain unreachable. This can create a sense of cosmic loneliness. But this is only one side of the story, because this same smallness also gives us an incredible perspective. Yes, we are physically a nothing in this universe, but we are also the only part of it that can understand it, that can ask questions about it, that can build tools to solve its deepest secrets. That structure 15 billion light-years wide is not aware of its own existence, but you are. Those massive galaxies cannot appreciate their own beauty, but you can. This is the greatest paradox of being human. We who are physically the weakest are the most powerful in the power of understanding. The James Webb Telescope is an extension of the human mind. Those golden mirrors are our eyes. Those spectrometers are our senses. Even though we cannot go to those distant lands with our bodies, we can go with our minds and our mathematics. You are a part of this incredible journey. As you read or listen to this text, you too are becoming part of the process by which the universe tries to understand itself. You are that rare and precious spark in this vast, silent, and indifferent cosmos that creates meaning. This brings us to a second contrast, the 13.8 billion year age of the universe and our fleeting human lifespan. On one hand, there is a galaxy that existed just 280 million years after the Big Bang, a structure that shone in the infancy of the universe, that created and saw generations of stars die. On the other hand, there is an average lifespan of 80 years, a moment shorter than the blink of an eye on the cosmic calendar. How can these two timescales come together? What does our existence mean on the almost eternal seeming timeline of the universe? This thought also has a tragic side, because it reminds us that no matter how much we learn, there will always be an infinite number of things we will never know. History flowed for billions of years before us, and it will continue to flow for billions of years after us. We are short-lived beings, standing on the bank of this vast river, able to see only a few drops. We will never know the ultimate fate of the universe, the answers to all questions. The time allotted to us is too short. But this limited time also makes every moment more precious, because we are here to witness this special moment of the universe. Right now, we are living in an era where for the first time in human history, we can look back to the beginning of the universe with such clarity. We are seeing things that giants like Newton, Einstein, and Hubble could not even have imagined. Our generation is the first to see real images of the first galaxies in the universe. Our generation is the first to witness the shaking of the fundamental pillars of cosmology. This is an incredible privilege. Yes, our time is limited, but in this limited time, we have the chance to read one of the most exciting chapters of the universe's 13.8 billion year story. You are a witness to this moment. Your existence, this short but bright moment, is the moment when the universe looks back at its own past. You are a part of that long and silent story, that brief but most important moment when consciousness was born and asked, why? And these questions bring us to a third contrast, the apparent emptiness of the universe and the deep connection within it. On one hand, there are galaxies billions of light years apart that will never reach each other. The cosmos appears to be mostly a cold, dark, and empty space. This might push us to the idea that we are alone in the universe. Each galaxy is its own island of stars, existing in isolation from the others. This is a tragic picture, because we humans are by our nature beings who seek connection. And this picture on the largest scale of the universe seems to show us an ultimate isolation, an insurmountable loneliness. But when we look deeper, the picture changes. Because the same laws of physics govern both the Hercules Corona Borealis Great Wall and the atoms in your body. That nitrogen forged in JADES-Z GS-Z14-0 billions of years later, became a fundamental building block of life on Earth. You are, in the most literal sense, made of stardust. Every heavy element in your body was created in the heart of a long-dead star. This means that everything and everyone in the universe is connected by invisible threads. Galaxies may be physically distant from each other, but they are all part of the same cosmic web, the same fundamental particles, and the same evolutionary story. We are not alone. We are the universe itself, and you are the living proof of this connection. The air you breathe, the water you drink, the thoughts you think, are all a product of this 13.8 billion year cosmic dance. You are a part of that great and complex structure that has gained consciousness. This is the deepest and most beautiful connection in the universe. But this connection is not just about the past, it is also about the future, and that future may depend on our choices. And therefore, this connection brings us to a fourth, and perhaps most challenging contrast: the certainty of what we know and the infinity of what we do not. On one hand, there is the incredible precision of the James Webb Telescope. It can measure the spectrum of a galaxy 13.5 billion light-years away, detect the amount of nitrogen in it, and calculate its rotation speed. This is a triumph of human intelligence and engineering. We can measure the Hubble constant with a precision of a few percent. We can map the temperature fluctuations in the cosmic microwave background with an accuracy of 1 part in a million degrees. What we know is built on a solid, tested, and evidence-based foundation. Science is the most powerful tool we have for unlocking the secrets of the universe, and it offers us a certainty and clarity we have never had before. This gives us a sense of control and confidence. But with every new discovery, with every new answer, we realize that we don't know much more than we do. This is the tragic part, because our hunger for knowledge is infinite, but our capacity to understand is limited. The cosmological principle was a fundamental assumption for 300 years, and now it is shaking. Dark matter and dark energy make up 95% of the universe, and we have no idea what they are. We don't know why the standard model is broken. We don't know how these massive structures formed. Beneath everything we think we know lies a vast ocean of ignorance. And the more light we shine, the better we understand how deep that ocean is. This is a situation that requires humility, because the universe was not designed for us to understand it. We are just a part of it, and we are subject to its rules. However, this ignorance is also our greatest source of hope, because if we already knew everything, there would be nothing left to discover. There would be no new questions to ask, no new theories to dream up, no new telescopes to build. Ignorance is the fuel of science. It is what drives curiosity, creativity, and progress. The shaking of the cosmological principle is not a disaster. It is an opportunity. It is a sign that the universe is more interesting, more complex, and more mysterious than we thought. It is a call that invites us to dig deeper, to think bolder, and to dream bigger. You are a part of this journey of discovery. You are an explorer facing this great unknown and searching for answers. Your curiosity is part of humanity's quest to understand the universe, and every why you ask is a small light we ignite in that great ocean. This brings us to what is perhaps the most personal point of this entire philosophical journey: the apparent meaninglessness of the universe and our ability to create meaning. On one hand, there is a cold, indifferent cosmos, governed by the laws of physics. The Big Bang, the formation of stars, the collision of galaxies. None of this happened with humanity in mind. The universe has no plan for us. There seems to be no inherent purpose to our existence. This can be an uncomfortable thought for some, because it can create a sense of ultimate meaninglessness. If we have no special place in the grand scheme of things, then what is the meaning of all our efforts, our joys, and our sorrows? This is one of the oldest and deepest questions of humanity. But the story does not end here. Because the universe itself may be meaningless, but we are not. Meaning is not something found in the universe. Meaning is something created by conscious beings, and we are the meaning-making machines in this universe. Art, music, love, friendship, science, all of these are our attempts to add meaning to an indifferent universe. The reason we built the James Webb Telescope is not because the universe told us to. The reason we did it is because we are curious. We want to explore. We want to understand. This is our greatest power. We are like artists adding colour to a blank canvas. The canvas itself may be empty, but the picture we create is not. You too create meaning in your own life every day, in the relationships you build, in the work you do, in the new things you learn. You too are showing resistance against this great meaninglessness. Your existence is a unique meaning added to this universe, and this is the greatest gift the universe has given us. Not to offer us a meaning, but to give us the opportunity to create our own. After considering all these contrasts, our greatness and our smallness, the infinity of time and the brevity of the moment, the emptiness of the universe and the connection within it, the certainty of what we know and the infinity of what we do not, and finally, the meaninglessness of the universe and our power to create meaning. We no longer look at the universe as just a series of physical objects and laws. We see it as a mirror, in which we try to find our own place. These discoveries are not just about galaxies and stars, they are about us, about who we are, where we come from, and how we find our way in this vast, surprising, and often confusing universe. But even after all these thoughts, one unanswered question remains, and this question is perhaps deeper than all the others, because it's not just about what we know or what we feel, it's about what we can become. And now it's time to ask the most internal question. What do we do with this knowledge? Because the universe may not have a plan, but we have a choice. When we face this new and confusing cosmic map, how does this knowledge change us? This takes us to a deeper layer of thought about our actions and our responsibilities. Now the question is not, who are we, but who should we be? Because these discoveries are reshaping not only the universe, but also the way we understand ourselves. This brings us to the first deep contrast between the power of knowledge and the limitation of action. On one hand, we have the ability to solve some of the most fundamental secrets of the universe. We can collect enough data to question the 300-year dominance of the cosmological principle. We can look back 13.5 billion years and analyze the chemical composition of a galaxy. We can detect the discrepancy in the expansion rate of the universe with 5 sigma certainty. This is an incredible power: knowledge, understanding, enlightenment. This is the power that has taken us from the ignorance of the Dark Ages to the light of modern science. We are beings who reveal the secrets of the universe, who make the unknown known. This is one of the greatest achievements of our species, and it gives us an immense sense of capability. But there is also a tragic side to this knowledge, because no matter how much we understand the universe, we cannot control it. We can know about the existence of the Hercules Corona Borealis Great Wall, but we cannot change its trajectory. We can know that the Big Wheel galaxy is 5 times larger than the Milky Way, but we cannot influence its star formation rate. We can know that the expansion of the universe is accelerating, but we cannot stop this process. We are like observers who understand the workings of a giant machine, but cannot press any of its buttons. This can create a sense of powerlessness, because knowledge does not always mean control. Sometimes it just means seeing more clearly how small and ineffective we are. However, this powerlessness also reveals our greatest responsibility, because we may not be able to change the large-scale fate of the universe, but there is one thing we can control: ourselves and this planet. If we are the only conscious life in the universe, then this consciousness is the most precious thing the universe possesses. Protecting it, nurturing it, and passing it on to future generations is our most fundamental duty. The universe's indifference to us does not mean we should be indifferent to each other and to our planet. Quite the opposite. It means the responsibility is entirely ours. You are a part of this responsibility. Every decision you make, every action you take, shapes the future of conscious life on this small blue planet. You are a representative of the universe's responsibility to itself. This leads us to a second deep contrast: the immutability of the past and the uncertainty of the future. On one hand, there is a 13.8 billion year immutable past that we see thanks to the James Webb telescope. The JADES-GS-Z14-0 galaxy shone that way 13.5 billion years ago. The Big Ring was formed that way 9.2 billion years ago. These events happened, they are over, and they are recorded on the frozen pages of history. We cannot change them. They are the unchangeable truths that form the basis of our existence. This gives us a sense of roots and continuity. We are the last chapter of a long and epic story. This is the weight of the past. But there is also a tragic aspect to this weight, because the past does not always determine the future. The story the Standard Model tells us is that the future of the universe is heading towards a cold, dark, and empty end. The expansion will accelerate. Galaxies will move away from each other. Stars will die out, and the universe will slowly slide towards a thermal death. This means the end of life and consciousness as we know it. This means that all our efforts and achievements will eventually dissolve into a cosmic nothingness. This is a sad and inevitable end. However, this inevitable end does not diminish the value of the present moment. On the contrary, it makes it even more meaningful. Because if our time is limited, then every moment we have, every interaction, every discovery becomes even more precious. Whatever the ultimate fate of the universe may be, we are here now. And now, we can witness this universe, understand it, and appreciate its beauty. Perhaps what matters is not how the story ends, but that we had the opportunity to be a part of that story. The future may be uncertain, but the now is certain. And the now is in our hands. You are a part of this now. Your present existence is that precious and temporary moment when the universe becomes aware of its own existence. Your consciousness is like a candle lit against that inevitable end. It shines for a short time, but as long as it shines, it illuminates the darkness. And this effort of illumination brings us to the third and final deep contrast: individual curiosity and collective knowledge. On one hand, there is the individual curiosity of Alexia Lopez, a single PhD student who started this journey. The questions she asked, the methods she developed, changed the direction of an entire field. This shows how much a single person, a single mind, can deeply affect our understanding of the universe. This is the power of the individual. This is the potential that lies within each of us. But there is a tragic limit to this individual effort, because none of us can solve this great puzzle alone. The knowledge is so vast, the questions so complex, that a single human lifetime, a single mind, is not enough to find all the answers. Every scientist stands on the shoulders of those who came before and creates a step for those who come after. Each of us is just a small drop in this vast ocean of knowledge. However, when these drops come together, they form an ocean. This is the most beautiful aspect of science. It is a collective enterprise. Alexia Lopez's discovery would not have been possible without the hundreds of years of astronomical observations, theoretical physics, and technological developments that came before her. Her findings are now being discussed, tested, and built upon by thousands of scientists around the world. This is the collective intelligence of humanity. It is the collaboration of people from different cultures, different backgrounds, sharing a common goal to solve the secrets of the universe together. You are a part of this collective effort. By learning this information, by sharing it, by thinking about it, you are also contributing to this great intellectual adventure of humanity. You may be a single drop, but without you, the ocean would be one drop less. But after all these thoughts, as we approach the end of the story, we find ourselves at a crossroads. And this crossroads brings us to one last question, perhaps the most practical one. And therefore, we now face the most practical question. In light of all this information, how should we proceed? This brings us to a final deep contrast between the fragility of our models and the resilience of the human mind. On one hand, we see how delicate even our best theories, our most complex simulations, and our most fundamental assumptions are. A principle that has stood for 300 years can be shaken by a few pixels of data. The Lambda cold dark matter model was the cornerstone of cosmology for decades, but now it is under pressure from all sides. This is the nature of our scientific models. They are not reality itself, but only the best current maps of reality. And like all maps, they are destined to be updated eventually. There is a tragic side to this, because it means we must accept that we may never reach the ultimate, absolute truth. There will always be the potential for the next telescope, the next theory, to overturn our current understanding. There will always be things we do not know. This can create a kind of intellectual restlessness, because the human mind desires certainty and closure. But the universe is not obligated to provide us with that. This means we have to live in a state of constant uncertainty. But this fragility is also the source of our greatest strength. Because our models may be fragile, but the human mind is not. Our minds are incredibly flexible, adaptable, and creative. When a model fails, we don't give up. We build a new one, a better, more comprehensive, more accurate one. The shaking of the standard model is not an end, it is a beginning. The beginning of a new physics revolution, a new era of understanding. This is the resilience of the human spirit. When faced with the unknown, we respond not with fear, but with curiosity. When we run out of answers, we start asking better questions. You are a part of this resilience. You too have the ability to question old ideas and embrace new ones. Your mind is a tool powerful enough to solve the most complex mysteries of the universe, and that tool is far more durable than our models. This brings us to the final thought at the heart of this entire journey: the contrast between the passivity of mere observation and the activity of exploration. On one hand, we could have simply observed the universe passively. We could have seen it as a distant stage, unchanging, incomprehensible, and indifferent to us. This would have been a safe position, because it would not require us to ask uncomfortable questions or challenge our comfortable assumptions. It would be just watching the universe flow by without letting it affect us. But we did not choose that. As humanity, we chose to explore actively. We were not content with just looking, we wanted to understand. We did not just observe, we participated. Building the James Webb Telescope is an act of participation. Alexia Lopez analyzing data is an act of participation. This is our effort to establish a dialogue with the universe, to listen to its story, and to add our own story to that great narrative. This is not an easy path, because this path is filled with uncertainty, disappointment, and the pain of abandoning our old beliefs. But it is also the most rewarding path, because this path teaches us something not only about the universe, but also about ourselves. It shows us how small we are, but also how capable we are. It shows us how little we know, but also how much we can learn. You are a part of this journey of discovery. By learning this information, you too are refusing to be just a passive observer and choosing to be an active explorer. You too are participating in that dialogue with the universe. We now know that the universe is a much stranger, much larger, and much more complex place than we thought. We are aware of our smallness, but also of our power to understand. We know the shortness of our time, but also our ability to make that time valuable. We understand that we are not alone, that we are in a deep connection with every part of the universe. And most importantly, we know that even when our models fail, our ability to wonder and to explore will never fail. As we approach the end of this long and deep journey, there is a place where all these discoveries, all these crises, and all these philosophical thoughts have brought us. It is not a list of answers. It is a new starting point. Because what James Webb has shown us is not just new galaxies and new structures. What it has shown us is an infinite horizon of discovery before humanity, and it is now up to us to determine the next step towards that horizon. Today, we saw how our most fundamental model of the universe was shattered, but I didn't tell you the real secret. Maybe this wasn't the first beginning. What if there was another universe before the Big Bang? What if we are just one link in an infinite cycle? On our next journey, we are going back before time. We will explore the cyclical universe. Are you ready?